Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on partial differential equations. And in particular I'm going to show you how you can solve some problems from PDE using Laplace transforms. Now in other videos I've shown you how to solve ODEs and associated initial value problems via an application of Laplace transforms. And so this naturally raises the question whether you can solve PDEs via this method. And the answer is yes. So this is the subject of today's video. And we're going to solve an example which is a linear PDE. It's just going to be first order and some associated boundary conditions. Okay, so this is the problem that we're going to look at. Now you can see here that one of the claims I've made is that the Laplace transform techniques are well suited to linear PDE with constant coefficients. Well, here the coefficient's not constant, but it's a function of x and not t. And because we transform both sides with respect to t, then you can treat x as a constant. So coefficients of x are okay. Now, just to refresh your memory, or if you haven't seen this method before, let me give you an overview of what happens. You start with a PDE and some conditions. You transform the problem via the Laplace transform. Here I've denoted it by this curly L. And what you do is you produce a transformed problem, usually an ODE. Then what you do is you solve this transform problem where this W bar represents the transform of the solution W to the original problem. And then what you do is you transform everything back to recover the solution to the original problem. Okay? So this to me is a general guide for solving problems via Laplace transform methods, or just transform methods in general. Okay, so we'll get to this problem a little bit later, but the first question is, what is a Laplace transform? Well, it's an integral transform. If you haven't seen Laplace transforms before, I just wanted to give you a quick introduction, and for those of you who have, just a quick reminder. So suppose I've got a function of one variable, so t might represent time, and this might be a solution to a certain ordinary differential equation. What you do is to take the transform, you take the original function f of t, multiply it through by an exponential, and you integrate with respect to t over the half line. Now with regards to notation, lowercase letters are usually associated with the original function of t, and uppercase or capital case letters are associated with the transform of the lowercase letter function. Now you can see in here that we're integrating with respect to t, but there's an s in there as well. So this notation emphasises that actually if we, for example, integrated this, you would be left with a function of s. Okay, so what happens if we have a function of two variables? So this w of x comma t might be a solution to a partial differential equation. Well, you can still define the Laplace transform very similar, except you have a function of two variables in here. And again, we use capital letters. Now, just to be very sure, I'm also going to put a bar over the W here, because sometimes when I write lowercase w and uppercase W, it looks very similar, especially when I'm writing it out by hand. So there's no confusion. I'm going to use a bar over the capital letter to denote the transform of the lowercase letter function. Okay, now if you want to, you can play around with this and put in various functions of t and compute this integral, or what's also very common is using a table to calculate transforms. Now, something I haven't mentioned yet, the f of t satisfies, it's piecewise continuous, and it satisfies some sort of exponential growth condition so that the improper integral will converge. Okay, even though I haven't listed that. All right, some important properties for our investigation today is going to be the transform of derivatives. So, in all of these transforms, I'm transforming with respect to the t variable. Okay, so you can prove these two expressions just using integration by parts. So you would put up here, you would replace w with w sub t, where the sub t denotes partial differentiation with respect to t, and then you would just integrate by parts. Okay, so in this sort of big W bar notation, this would be, oops, sorry, it's just S. This would be the following. And down here, this would be the following. So this is what happens if we take the Laplace transform of a second order derivative with respect to t. And what happens if we're taking the Laplace transform with respect to t of an x derivative? Well, it's just the derivative of the transform with respect to t. Okay, so to prove that, you can use Leibniz rule for differentiating under the integral sign. So if I was to take this and oops. So just go up there and replace this with w sub x. See if I can squeeze it in. Okay, I'm just going to drop off the argument there just to save a bit of space. Now, this derivative can be shifted outside the front of the integral sign. So I'm sort of using Leibniz rule in reverse here. Okay, what is this? This is just this. So it's the derivative of the transform. Okay, and if you're transforming the second derivative with respect to x, then that would you'd have a d squared, dx squared there. Okay, so these are important properties known as transforms of derivatives that we'll use and apply when we're solving our problems via Laplace transforms. Okay, so let's have a look at the following problem. Solve via Laplace transforms. Okay, so we've got a first order problem here. Coefficient is a function of x. You've got some extra conditions known as boundary conditions. And let's just follow this model here. Transform the PDE, produce a transform problem, which is essentially an ODE, an ordinary differential equation. Solve for solve the transform problem, and then invert everything via an inverse transform. Okay, now just to mention, the inverse transform is an operation that undoes the Laplace transform. So if I transform something and take the inverse transform, I get what I started with in, and you can switch it around. Okay. Now the inverse transform, to really write down an explicit representation for it, you need an understanding of complex analysis. So I'm going to assume that you don't have a deep understanding of complex analysis. So we can do these problems without knowing exactly what the inverse transform is. Okay. All right. So let's follow this guideline here. Let's transform everything and produce some sort of transform problem. All right, so I transform both sides, and because it's an integral operator and essentially it's a linear operator, I can break up the left-hand side, and even though I'm taking the transform of this, we're transforming with respect to t. So we imagine that x is essentially a constant here. Transform of 0 is 0. Now what I can do is simplify this a little bit by using my transform of derivatives. Okay, so up here I'll get that, and I've got this as well. So TOD is going to stand for transform of derivatives. Okay, so over here this is just the derivative of the transform. And this here is this minus this. Again, I've just left off the arguments here and here for just to save a bit of space. Okay, well, let's look up to our conditions up here. We can use this in here. We know that this is 0, so that term's going to disappear. Okay, so that's going to be 0. And we get the following. So we can see that we've actually reached this stage now. We've produced a transform problem, which is essentially an ODE. Why is it an ODE? Because it's a PDE where only one derivative is present. Okay, so let's see if we can solve this transform problem. So that's what we're trying to do now. Okay, we're at this stage. So let me just make a comment there. This is essentially an ODE. It's first order. Linear and separable. So what we can do is solve this just using ordinary differential equations techniques. So how do we do it? Well, we know that the solution to this is going to be something like an exponential function. Okay, so imagine s is a constant here. Okay, we want to solve this for w bar. Okay, so you look at the coefficient of w bar, and because it's on the left-hand side of the equation, you would take e to the integral of the negative of that coefficient. Okay, and then you would have what's something like a constant of integration here, but because w bar is a function of two variables, this really should be a function of s. Okay, so if I do this integral with respect to x, I'll get the following. Okay, imagine s is a constant. All right, so I now have a general solution to this problem. So I've almost solved for w bar, I've almost solved the transform problem, but I haven't found this a of s. Now I've used this, but I haven't used this yet. So to find this coefficient, we're going to use this. Okay, so me just this is the general solution, W bar. Okay, now let's obtain A of S by the following. Well, if I transform this, I'll get W bar of 0, S. Okay, what is the Laplace transform of t? Well, it's 1 on s squared. Now you can work that out either directly or from a Laplace transform table. Okay, so now what I can do is go up here and go, okay, well, when x equals 0 in here, I'm going to have e to the 0 times a of s, which is just a of s. And I know from this condition that w bar of 0s is 1 on s squared, so I could team those up. Okay, so that and that with x equals 0 gives us my coefficient. Okay. So we've now solved our transform problem. So we've completed this step. Let's move to recover W, the solution to the original problem. We've solved the transform problem. Let's get back to the original setting now. Okay, so to do this, we need to take an inverse transform. Okay, so how do we do that? Well, we want to take the inverse transform of both sides. Now there is a theorem from Laplace transforms which gives you the inverse transform of a function of x times an exponential function. Okay, that is called the second shifting theorem. Okay, so we're going to apply that and we'll get our solution W. Okay. Via the second shifting theorem. Okay, what is the second shifting theorem? It's the following. If I have a function of s times an exponential, and I want it, and here a is a constant, and I want to take the inverse transform, it's the following. Okay. The inverse transform of this product is just a Heaviside step function shifted times g of t shifted, where g of t is the inverse transform of this function. Okay, so for this, g of s would be 1 on s squared, a would be x squared, and essentially what you want to do is compute the inverse transform of 1 on s squared, shift it, and then multiply through by this Heaviside step function. Okay, so let me show you how to do that. Oops. Okay, so g of t equals the inverse transform of 1 on s squared. Now the inverse transform of 1 of s squared is t. You can look that up from a table. And so applying the second shifting theorem, the inverse transform of this it's this shifted, so I'll replace a with x squared, and then times g of t minus a. So g of t is t, so I replace t with t minus x squared. Okay, so what is this unit step function or Heaviside step function? Well, when t minus x squared is less than 0, this thing will be 0, so the whole thing will be 0. When t minus x squared is greater than 0, this becomes 1, so the whole thing would be, sorry, g's just the identity function here. Okay, so you don't need that g there. Okay, let me put in some square brackets. Okay, so this will be 0 when t minus x squared is less than 0. It'll be 1 times this when t minus x squared is greater than 0. And what happens when t minus x squared equals 0? Well, in my videos I define this to be a half. But it doesn't really matter because that's going to be 0 anyway. So you get a half times 0. So it's just 0. Okay, so I've managed to squeeze everything onto that page. You can see now that we are at the final stage. We've recovered W, the solution to our original problem using an inverse transform. Okay, so there you have it. Now the steps for these kinds of problems are the same. Start with your PDE, transform it, include some of the conditions, produce a transform problem which you can solve by incorporating other conditions. Once you've got your solution to the transform problem, you transform everything back by an inverse transform. Okay, and you recover the solution to the original problem. So going from here to here, tables are useful. Okay, sometimes you can compute inverse transforms without tables, for example using residues from complex analysis. But in this presentation I'm just assuming that you're working from a table. Okay, so I hope this presentation's been useful. In upcoming videos I'll solve some second order problems. Now I know you can solve this problem perhaps using method of characteristics or other techniques. So what I'm going to do is show you how to apply Laplace transform to solve second order problems. I hope you can join me for those presentations.